Now the splay trees. The target of the splay trees is a little bit different than the target of ABL tree. It says that any m consecutive tree operations, no matter what that operation is, like insertions or deletions or find or whatever, starting from an empty tree, take at most big O of m times log n time. Let me ask this question first. Is ABL tree a kind of splay tree? And the answer is certainly yes. Because what? Because if we have an ABL tree, every operation, no matter what that operation is, the time taken to do that operation will be big O of log n for every operation, because the tree height is guaranteed to be big O of log n. Certainly for sure, given m consecutive tree operations, the total time will be big O of m times log n. So if we have an ABL tree, we have a splay tree, but not the other way around. So does it mean that every operation takes log n time, just like what we have in ABL tree? And the answer is not really in splay tree. It just means that the amortized time is log n in the splay tree. What does it mean? What is amortized time? Do you know? In Chinese, we say this is 摊还时间. But I guess still you have no idea about what 摊还时间 is, right? A simple explanation would be like, we can say amortized time is like our average life quality. Say, if we are in good luck and we have a lot of incomes at the current time, and we would like to save some money in a savings account in a bank, and therefore later on, in case we encounter bad luck and we don't have any income, say, we can still withdraw money from the savings account. So to keep our life quality in a certain level, and that certain level is called amortized level. But anyway, we're going to come back to that topic later, so let's just move on. But it means that even though the amortized time is log n, but still a single operation might still take the worst case, like the linear time. Then what's the point? Well, the point is, although that the worst case bound is weaker, the worst case bound is big O of n, not log n, but the overall effect will be the same, which means there are no bad input sequences. No matter in which order that we do insertions, the total time would be the same as we have for ABL tree. The total time will still be m times log n, even though it's possible that for one operation it can be as bad as big O of n. But so if one node takes a linear time to access, we can keep accessing it for m times and get something like big O of m times n, can we? Well, it just means that we cannot let that happen. How can we avoid that? Sure we can. That only means that whenever a node is accessed, it must be moved. If one node is the worst case for one operation, next time it better be the best case, so that the amortized time, or say the average time, can be at least better than linear, which means this node has to be moved to somewhere else. But to where? The solution given by the splay tree is this. Okay, the idea is, after a node is accessed, no matter where that node is, it is pushed up to the root by a series of ABL tree rotations. So that's why we say that splay tree is closely related to ABL tree. It's weaker than the ABL tree, but it uses ABL tree rotations. And the next question is how? We know that we have at least two kinds of ABL tree rotations. What if we only use single rotations? So here's one example. So let's first try to access the key 1. Okay, After key 1 is accessed, let's use single rotations to move key up to the root. So step 1, rotate K1 with K2. Okay, and get something like this. And rotate K1 with K3. So K3 is down. Now rotate K1 with K4. So K4 is down. Now finally rotate K1 with K5. And that's the tree we obtained. But notice here that although some of the keys are in a better position, but some other keys like key 3 will be pushed down to a deeper position. So basically single rotations doesn't work. And this is not the worst case. Let's look at another example. An even worse case. Let's input 1, then 2 next. 2 should be pulled up to the root. So after the single rotation, we're going to obtain a tree like this. Next, let's try to insert key 3. What's going to happen? 3 will be rotated up to the root position, and we obtain a, you can see the shape, a skewed tree, right? Let's keep doing so until we get n, and we're going to obtain a skewed tree with n nodes like this. But this is not so bad so far because each insertion only takes a constant time. We make one insertion and one rotation is constant. So with n insertions, the total time is big O of n. It's quite good, not bad at all. But let's try to find one. What's going to happen? We're going to start from the root and take n steps to find one. And then we must apply single rotations to rotate 1 up to the root. So after the rotation, we obtain a tree like this. Next, let's try to find 2. What's going to happen? We're going to take n steps to find 2 and rotate it up to the root and get a tree like this. Alright, now keep doing so until we find n. We're going to get back to this skewed tree. So what is the total complexity for these n operations? It's going to be n squared, right? So it doesn't work. Does it mean that we should just abandon the idea of using AVL rotations? Certainly not. Let's try again. Besides single rotations, we still have double rotations, right? So for any non-root node x, let's consider not only its parent, but also its grandparent. Look up for 2 steps. Okay, basically we're going to have 3 cases. Case 1 is that it has no grandparent. Its parent is the root. Then it's going to be simple. One single rotation, rotate x and p, make x the new root. And case 2 is that p is not the root and therefore it has a grandparent. And then there are 2 cases here. One is the zigzag situation. Zigzag situation. If this is the zigzag situation, we just make a double rotation. And this is the resulting tree. And if it is the zig-zig situation, so this is zigzag, this is zig-zig. For the zigzag situation, we just do a single rotation to move x up to the root. So that'll work. Now let's get back to the previous example. Let's access K1. So the first one is a zigzag situation. And we're supposed to do a double rotation. And that will be the result. And next, it will be a zig-zig situation. So that will be the result. We can see that the height of the tree is almost halved. And this is actually the common case. It says splaying not only moves the access node to the root, but also roughly halves the depth of most nodes on the path. Now let's check the previous worst case. Let's insert 7 nodes and we obtain a skewed tree like this. Alright, now let's try to find one. What's going to happen? We're going to first handle a zig-zig situation for 1. And another zig-zig. And another zig-zig. So when 1 becomes the new root, the height of the tree is almost halved. And there's another example given in your textbook. It's a 32 node example. So you can take a look when you get the book. So far we have only talked about insertions. How about deletions? Deletion is actually quite simple. Step 1, in order to delete some x, we have to find it, right? Since we're talking about a splay tree, after finding this one, this node will be at the root position. Then deleting x turns into deleting the root. Okay, so we remove the root. After removing the root, we're going to obtain two subtrees, left subtree and right subtree. And what else can we do? We actually have two options. Right? We can either change the left subtree or change the right subtree. Now let's change the left subtree. Called find max. Find the max key from its left subtree. What's going to happen? The max element in the left subtree will be rotated up to the root position, right? So the largest element will be the root, the new root of the left subtree. And this one must have no right child. Why not? You can prove by contradiction, right? If it has a right child, the right child has to be larger than this root. But the root is already the largest one, so it's impossible to have any right child. And what else can we do? Simple, right? Just make the original right subtree the right child of this new root of the left subtree. So everything's going to be fine, meaning that it's still a binary search tree after the deletion. And one last question about splay trees. Are splay trees really better than AVL trees? This is not a simple question. I would suggest you to first implement both trees. Well, say, what is so good about splay tree comparing to AVL tree? Because splay tree is simpler. When you implement splay tree, you can realize that it's much simpler than AVL tree because if we use AVL tree, we have to always keep an eye on either its BF or the height, right? But if it's a splay tree, we don't care. We don't care whether or not the tree is balanced or not. We simply blindly do rotations. And the overall performance will be the same as the AVL tree. So it sounds like the splay tree is better than AVL tree, but is it really so? Do some tests, and I hope you can find the answer by yourself.